Yeah. Okay. So now I want to start talking about what we can do with entropy. So we have to properly define it, but I hope I gave you the motivation of what the definition should be. Definition X be a random variable taking values in some countable set . So this means that we have some probability measure in the background, probability space, and X is a function from omega to G. Okay, measurable function. Since that it pulls back, it's countable here, but just pull back singletons to events. And we could also look at probability measures on G. It would be the same thing. So alternatively, maybe I'll do it in two colors so I can get everything down at once. Alternatively, it's the same exact definition. Mu is a probability measure on G. And what is the correspondence between mu and X? Mu is the law of X. So mu of a little x is the probability that big X is equal to little x. Okay, this is the correspondence between the two things. Then we define the entropy of X. Gibbs, Shannon, whatever you want. So entropy of X and alternatively mu. Okay, by h of X. This is just going to be a number now. Okay, this is just going to be a number. It's not an all random. And this is also h of mu. And the way we define it, well, we already saw what we need to do for probability measures, right? We just sum over all possible probabilities, and we take p log p or mu log mu, and put a minus sign, just so that everything is non-negative.
Wait, so how does mu relate to X again?
So mu, you could think that, so these two things will be exactly the same. I'm going to write down this for X. Okay, but these two things will be exactly the same if we just define mu to be the law of X. Okay? But I just wanted that you can define it for probability measures, you can define it for random variables. It's the same thing. So h of X is just going to be h of the law of X, which is minus some little x, probability big X is equal to little x log the probability. You have to notice that this thing, what is it? It's an expectation. It's an expectation of what?
Log p of the log of the log.
Yeah, so if we define the real valued random variable y to be just how am I going to write this? Yeah, so
Y of X.
yeah, okay, so yeah, okay, so if mu is the law, we could define y to be mu of X. So X is a function from omega to R to G. Mu is the law of it, and Y is mu of this random thing. So Y is random. Now Y is a random number. And what we're doing is we're just looking at the expectation of minus log Y. Okay? Now Y is a number between 0 and 1. So this expectation lives, this is a non-negative. This is a non-negative, always a non-negative random variable, minus log of y. And so we can take its expectation, but it could be infinite. could be infinite. Okay? Have to be careful, it could be infinite. It's well defined, but it could be infinite. Okay?
But you're saying that the expectation of minus log y is exactly the entropy, right? Yeah.
Yes. Just giving a different perspective. It's an expectation. This entropy does not care about who the actual values of x are. Is x taking values in some group, in some set, in some space? I don't know what. It just cares about the probabilities, the numbers, how x is distributed. Okay, it only looks at the distribution. It doesn't look at the actual values. Okay, so it's a property of the distribution, not a property of the specific values. If you have a uniform distribution on chairs, on 10 chairs, or you have a uniform distribution on 10 students, they will both have the same entropy. Because only the numbers are important. These 1 over 10. That's what's important. Okay. One more thing is that with this notation, we have a convention that 0 log 0 is 0, which is the continuous extension of x log x. Okay. Just a convention that 0 log. So I could specifically write out only sum over things that the probability is positive, but can just take the convention of 0 log 0 is 0. You have to be careful with log 0. It's minus infinity. Okay, so this is the entropy. Okay. Now, as I said before, you should think about entropy as kind of information content. How much information does this distribution carry? So we could also define conditional entropy. Okay, how do I define conditional entropy? What does this mean? So here, X is as before, and F is a sigma algebra in the probability space that I'm talking about, right?
When you make something conditional, that makes it become a random variable, right?
Yes. Well, not here. Entropy
Not
is
here?
not here. So I'm going to find. So what is conditional entropy of F? This is going to be not a random object. It's going to be the expectation of the conditional entropy, the random conditional entropy. So I put the F on the bottom. Okay, this is random. I'll take expectation. And this is random because conditional expectation is random. So what is H, F, X? Well, this is just what I do is I have the information in F. This gives me a random probability distribution of X, right? So this is just going to be the entropy of the conditional probabilities of X. Let me write it this way, conditional. This is a random probability distribution. Right? You understand what I mean? I put a dot here. I just mean this is this. So when I give you F and I look at this conditional thing, right? This is a probability distribution for every little omega, right? It's a random probability distribution. So I can take its entropy. This is a random variable. The entropy is a number. It's a random variable, right? Associated to a random probability distribution. Function of omega. It's function of omega because this conditional thing is a function of omega. Okay? And then I take the expectation of that for my conditional omega.
I guess conditional expectation of
yeah, so this is as we said this before, this is the conditional expectation of the indicator of the event that X is equal to something conditional on F. This is the same thing.
When you write it like that, that means you're taking the H mu, right? Because this is a probability.
Yeah, okay, so again, I take an F, then I have a random probability measure, mu F. Okay, I could call this thing, I could call this mu F. What is it? It's a random probability measure, right? For every little omega, this gives me a probability measure.
But not omega, like elements of G.
No. All of this is a function of omega. This is a random number. It's not a random number. If I plug in an element of G, I get a random number. Those random numbers will sum up to 1. Then I sum over G. So when I leave a dot here, when I'm looking at this whole vector, this is a random vector which sums up to 1. It's a random probability distribution. I can measure its entropy. That's a random entropy. A random variable, it's a random number. Then I can take its expectation.
And this conditional expectation of indicator of x equals something with respect to f, it's not the same, it doesn't have the same distribution like expectation, the conditional expectation of x with respect to f?
No, this is a number. X is valued in some group.
Yeah.
I cannot take expectations.
Oh,
This is a list of numbers, one for every G,
Mhm.
and I can make them random.
You take an omega, you plug it in, you get some probability distribution, and then you get an entropy.
Yeah. And then I take expectation.
Yes.
Okay? Now, exercise. Okay? One more definition. If I have two random objects, h of x and y, then I can define the conditional entropy of y as the conditional entropy of x conditioned on the sigma algebra generated by y. This is all the pullbacks, right? Pulling back all the everything, generating everything by pulling back a single. Okay? So x and y here are taking values in some countable set. Okay? So this defines it. And the exercise is to show that h of x conditioned on y is equal to the joint entropy minus the entropy of y. What is this? What is joint entropy? Well, this is just a pair of random variables taking values in what? In G squared. That's still a countable set. Right? So you can just measure the entropy of that. Right? I can always put in vectors of these guys, right?
X equals X, Y equals Y.
for the pairs.
Yes. Y,
Yeah, so
X, Y equals X.
let's compute what this is. Just I want you to see that these are okay. Okay, so let's compute. So this is the exercise. The exercise is to show that this, from the conditional expectation, where does it come from? It comes from the fact that y has a partition, right? We can write all of these things as partitions. Okay, so it's easier to, right? Because what happens when I condition on the sigma algebra? Let's go back to the original. What is the probability measure? Probability measure is random. What does it do? It samples y. Oh, if I know y, then what do I have? I have the conditional distribution of x conditioned on that specific value of y, right? Which I can always define in the discrete case, right? And then the conditional distribution has an entropy. And then I average over all the possibilities of y. Okay? So this is why, so this is how you get these two things. But let's write down what these are. What's written down here is the sum. Here it's the sum over all pairs x and y of the probability that x is equal to x, y is equal to y, log, let me write it this way, 1 divided by the probability x is equal to x, y is equal to, right? That's,
Instead of the minus sign.
yeah, 1 over is instead of,
So just if it's 0.
yeah, so I said 0 log 0 is 0. Okay. If you want, I can put the minus.
Okay.
You don't have the zeros in the sum. You don't actually have the zeros. Okay? So this is this, and I have minus hy. What is minus hy? It's plus sum over y, probability that y is equal to y, log probability that y is equal to y. Okay? Now, what do I do with this thing? Well, what you can notice is that
Multiply the log and the log.
I can change this into a conditional expectation, right?
Like condition on it.
Yeah. Right, so I can change that into conditional expectations. What I get this is just different ways of seeing the same thing. I mean, write it down. That's how you get all of these things. So this is equal to the sum over x and y probability that x is equal to x, conditioned on y is equal to y. Let me do it this way. Sorry. This is the sum over x. The sum over y is here. Probability that y is equal to y. Right? Okay. Remember, as soon as these are zero, I don't count them. So I'm just going over the non-zero one. Here I have the log of what? I have the, okay, so I have log, okay, let me write instead of minus just 1 over. So I had probability x is equal to x, y is equal to y. So I can turn that into a conditional, but remember that log of a product is sum. So I get that I get another term, which is this. Right, so these two terms gave me the first entropy term. And then I had another term, which was the sum probability y is equal to y log probability y is equal to 1. Okay? Now let's see what happens. Let's see what happens. What is the sum over x probability x is equal to x conditioned on y is equal to y? What is this sum? This does not have an x in it. It comes out. So this sum gives me 1. Right? It's just summing over all the possibilities for x. Conditional distribution. But then I have sum of p log p in minus sign plus p log this. So these two disappear. Right? So what's left is, remember we're computing the conditional expectation. Again, I want you to notice what's going on here. Inside the little y, when I fix little y, I have an entropy, right? Because this is a conditional distribution. This is a conditional distribution. I'm doing p log p, right? So what I have here is the expectation of the entropy of the distribution of x conditioned on y. Right? You take the average over this y. When you condition on y, big Y equals little y, you get exactly the entropy that's written there. Right? So this is this entropy.
Can you repeat that, please?
Okay, let's do one more step. So outside I have sum y, probability that y is equal to y. Okay, so this is an expectation of something. Of what? What's written on the inside? There is some distribution over x, right? Little y is now fixed. There's some distribution over x of p log 1 over p, which is entropy. Entropy of which measure? It's entropy of the measure, which is the probability x is equal to something, conditioned on y is equal to 1. Right? This is a probability vector. I can take its entropy. Now, this entropy depends on the little y, and I'm averaging over the little y's. So what I have here is an average of the entropy of the random measure, which is the probability that x is equal to something conditioned on y. And I mean, you can see that this is exactly what I want. Okay, so we can actually write out the expression. This is the expression, and I just really write it out specifically. Sum over y, sum over x, do all the, write it out explicitly. You can always write things out explicitly in entities. Remember, some things here could be infinite. You have to be careful. Okay, this is not well defined. This is not well defined. If this is infinity and this is infinite, you have to be careful. Okay. So everything here is under the assumption that they're fine.
If one is infinite, if one is finite, that's fine.
So yeah, it still will be fine. But if this is infinite, then this will also be.
Oh, okay.
And it basically comes out from what we just. Now, what I want you to notice is that we get a few consequences of this. Corollaries. h of x conditioned on anything is less than or equal to h of x.
Like when you have some information, you
If I gave you information, and this is very good to think about sigma because it's information. If I gave you information, then you need then the entropy carries less information.
the entropy is what you don't know.
Entropy is how much information does this distribution of x carry. If you already know something, then definitely it doesn't give you more information than what it would have given you without knowing anything. That's the way you should think about it. If you know y, then the conditional distribution of x given y will not give you more information than just
knowing it.
telling you what x is. Okay? Another thing is that if you put those together, is that if you take the joint entropy of two random variables, then it's less than or equal to, well, it's equal to h of x conditional on y plus h of y, but that's less than or equal to h of x plus h of y. Okay? Exercise. I'm not going to solve this, but I got the equality case. Okay? These are basically just Jensen's inequality. Basically, if you think about these things, what we've done is just Jensen's. Okay? But exercise, show h of x conditional on f is equal to h of x. So equality case, and this is including the case where f is just sigma algebra generated by y, if and only if x is independent which is the same as saying that h of xy is equal to the sum of h of x and h of y, if and only if they're independent. Okay? Another exercise. So these are standard exercises. You should go through them. They're all basically applications. So for this one, you actually, when I told you you're doing Jensen, you need the equality condition in Jensen, right? Jensen has an equality. When things are equal. Okay? Things are equal, then you should say that something is constant. What else do I want you to know about entropy? Yeah, if the sigma algebra is trivial, so if f is trivial, i.e. probability of A. So we have some probability space in the background, right, which we're talking about. Probability of A is either 0 or 1 for every A in F. So this is what a trivial sigma algebra, I mean, it's an extension of what I would call the trivial sigma algebra, but so all events have probability either 0 or 1. There's no really information in F, okay? So if F is trivial, then what is the conditional entropy of, if I give you F? It's the same. I didn't give you any information. Okay.
Even intercoronary or less.
Because probability 0, 1 events are independent of everything. Yes. Yes. Okay. It is a curve, but just wanted to point out. Okay, so these are the exercises you should think about and try to prove. let's do together a better exercise, which is very interesting. Okay. So this will solve together. If for finite f, so if x lands in some finite set with probability 1, okay, then the entropy of x, what is the maximal entropy on a finite set?
Log X.
Log the size of the set, which is the same as the uniform distribution. This is, I'll write this right in a different color just to stress that the maximal entropy is attained on finite sets is attained by uniform distribution, and you cannot say that for infinite sets because there is no uniform distribution on infinite complex. This is equal to the entropy of uniform on F. And uniform on F just means uniform on the number of F elements, right? So all uniform distributions on the same amount of elements are the same in terms of entropy. The entropy does not care about the specific set, it cares about the values of the probabilities. Okay, so we'll do this in a second. It's just yet says inequality. But moreover, if there exists a function from G to finite subsets, being a bit informal here, I could have defined finite subsets of G, right? So this is a function that for every element in my target set G gives me a finite subset of G, okay? Just some function. If there exists a function such that the probability that x is inside this pi of y equal to 1, so it could be a different finite set for every different little y, okay? And these do not have to be uniformly bounded. These guys, right? So you've got bigger and bigger sets. If you know that with probability 1 you have some control over where x lands in finite sets, then the conditional entropy given y, so if you know where you landed, right, what is the most entropy you can have? Log. This is going to be less than or equal to log the size of 5y, right? This is a finite set. I can measure its size, I can measure its log. What is wrong with what I wrote? I wrote something which is what?
This is random.
This is random, this is not. Right? Okay. This is an extension, of course, right? Because you could take 5y just to be, you could take y to be a trivial random variable, and phi is just constant, right? Right, and then the entropy of x is exactly the entropy of x conditioned on y, because y is a 0, 1 thing, and so you have entropy of x. So this is an extension of this. Okay, but I'll use the first one in the proof. Okay, so the first thing I'm going to leave to you as an exercise. So h of x is less than or equal to log f if this is an exercise for you to solve. We basically did it before with the p's and the q's. Just showed if something is use Jensen's inequality on minus log, like that. Okay, and let's prove the other one. Okay, so let's do h of x conditioned on y, the second one. Okay, so I'm assuming that x lands in a certain finite set, which depends on the value of y. Y is some random thing. It's kind of the random thing. Okay, what am I thinking about? Let me tell you what I'm thinking about here, just so that you have it for the future. I'm going to think about the following situation. I have a random walk at a certain time t. Okay, now this random walk comes from a measure which is not finitely supported. So I don't know that it's in a certain ball. of radius, I don't know, constant times t. All I know is that, and so y is going to be the distance of xt to the origin. So I know that if I know the distance to the origin, if I know it's 10, I'm in the ball of radius 10. If I know it's 20, I'm in the ball of radius 20. So there's some number which governs what is the finite set that I'm in. So the conditional entropy will be less than expected log the size of the ball. That's what it's going to be. Okay, but we're doing it in maximum generality, right? So now, conditional entropy given y, we have to write it out. We saw already what this is. This is the expectation under y of the entropy of the conditional measure of this.
So there are some proof problems.
Hmm?
Never mind.
Right? Maybe we could have done it in a more fancy way, but I want to explicitly write everything down. Now, what is this distribution? What do we know about this distribution? We know, or we're given, right, that the probability that x is in phi of little y, conditioned on y is equal to y, this is 1. Right? We know that x always lands in the set phi of 1. That's the assumption. So this means that the conditional distribution here, this fixing the y, the random, another random, fixing the little y, the vector, the probability vector that we get for these numbers, right, is one that lives inside a finite set, which is phi of 1.
Up to measure.
And in this thing, we have the entropy, right? So what does that thing say? That thing says the average, right? So in this thing, this says the average over little y. Yeah, up to measure 0, but I don't care about measure 0 because the measure zeros don't appear in this line.
Like, why is that true? We know that the probability that x is in Fy is 1. Why is it still true when you take conditional? Y equal to y?
I mean, you can turn this into an intersection. So it's this intersected with this, divided by probability y is equal to y, right? And you know that the top one has probability 1, so you just get the row quotient. Right? Okay? So so this is the average over these guys of what? Of the entropy of this thing. Right? Little y is fixed. This is a probability vector, and I can take its entropy. But from part 1, this vector, right, takes value. The guys you can plug in here are only finally many guys coming from the phi of y, right? So this is less than or equal to by 1 by the first assertion. You see why I'm extending and I need to use the first one, right? This is less than or equal to the average over the y's of what is the maximal entropy for something that takes in value y log
Size of
phi of y size, right? That's what we know. And this is, of course, exactly what I wanted. This is the expectation. So you see where the expectation is coming in, right? Log. It's very easy. I mean, you always can write things out. Basically, this is important. Okay, so we'll use this next time to give some estimations of random walk entropys. This is basically what you always do. You find a set and find it. In fact, even some boundary theory. It's Kaimanovich criterion. If you know what it is, and if you don't, forget it. What?
I can repeat that.
There's a Kaimanovich criterion how to determine the Poisson boundary. Basically, that's what's going on. You're conditioning on something, it gives you information, it bounds how big the set could be, and that thing goes to 0. That's how this is typically used. Not the criterion itself proving it. The showing that something is 0 is usually shown by giving some boundaries. Entropy is very easy to work with these bounds because of all these inequalities. Basically, Jensen's inequality is giving us a lot of tools on how to control things. Okay.
This one I know, the if I remember. I'll try it.